We've talked about probability distributions with different shapes, including the normal distribution that looks like this. We've also talked about skewed distributions where the distribution is left skewed, where we have the tail on the left and then the big hump that comes up on the right-hand side. And then right skewed distributions where we have the big hump on the left and the tail on the right-hand side. I want to spend some extra time focusing on normal distributions and some other things that we know about them because normal distributions come up all the time in both probability and statistics, so they become extremely important for us to understand in detail. So again, this is a probability distribution curve for normally distributed data. The mean of a data set for normally distributed data will always fall right in the middle of the normal distribution. So the mean is right here at the center. This is also where the median is located. So both the mean and median will divide the area under the distribution curve in half exactly. Remember also that the area under a distribution curve will always be equal to 100% or 1.0 if we write it as a decimal. So we really have to think about the area under the curve in terms of percentages. For example, because the area under the curve will be 100% of the probability, we could say that we have 50% of the probability to the left of the mean or median, and 50% of the probability to the right of the mean or median, because we have 50% of the area to the left and 50% of the area to the right. Similarly, normal distributions follow what's called the empirical rule. So we'll go ahead and write down here the empirical rule, which is also called the 68, 95, 99.7 rule, which is a funny name for a rule, except that it's very practical, because what it tells us is that specifically for normal distributions only, we'll always have approximately 68% of the area within one standard deviation of the mean. In other words, let's go ahead and say, for example, that one standard deviation away from the mean looks like this. So if we head from the mean and we head in this direction, this distance is one standard deviation, sigma. And then in this direction, the exact same amount of distance, we have one standard deviation. So one standard deviation to the left, one standard deviation to the right. And what the empirical rule tells us is that 68% of all the area under the curve is going to be in this interval. So between these two outer lines here, between one standard deviation to the left and one standard deviation to the right of the mean, we're going to capture 68% of the area. If we go 2 standard deviations away from the mean, so we could think about this here as 2 standard deviations away from the mean on the right, and then over here, 2 standard deviations away from the mean on the left, that the area under the curve between this line on the left and this line on the right is always going to be 95% of all of the area under the curve. So almost all of it, everything but 5% of the total area. And then within 3 standard deviations of the mean, so again, if I go from the mean over here to the right, a distance of 3 standard deviations, and then over here to the left, a distance of 3 standard deviations, that the area under the curve between this line on the left and this line on the right is going to be 99.7% of the area. Now, the empirical rule is really powerful because now that we understand that the area under the curve is 100%, and the empirical rule lets us divide the area into different percentages based on standard deviation, we can say things like this. Well, if 99.7% of the area is between 3 standard deviations to the left and right of the mean, then that must mean that the little tails here at the end, outside of 3 standard deviations, together is only going to make up 0.3% of the area, because we can take 100% minus 99.7%, and the result there is 0.3%. But we have the two tails, the one on the left and the one on the right, and they're equally divided because remember we have an equal amount of area to the left and right of the mean and median, and this distribution is symmetrical. Normal distributions are always symmetrical, which means that the area in this little tail on the right here is exactly half of 0.3, or 0.15% of the area. And then same thing over here on the left-hand side, this is 0.15% of the area. Since we know that one standard deviation away from the mean on either side captures 68% of the area, if we just wanted to know this area right here of this region, that would be half of 68%, or 34%. Or if we wanted, for example, to know the area under the curve that's outside of one standard deviation, but within two standard deviations, that would be the area of this region here plus the area of this region here. Well, how would we find that? Well, we know that within two standard deviations, we have 95%. So we could say 95%. And then within one standard deviation, we have 68%. So we could say minus 68%. And the result there is 27%. 95 minus 68 is 27. Then if I wanted, for example, just this area here, that would be exactly half of 27%, because the 27% again is this region plus this region here. But if I just want one side, I would take half of that. 27 divided by 2 is 13.5. So I know that this area here is 13.5%. So we can do all kinds of area calculations like that using the fact that the area under the curve is 100% and what we know about the area within each standard deviation from the empirical rule. So just keep that in mind because we'll use this over and over again to calculate specific portions of area under a normal curve. When we talk about a normal curve, we can also talk about percentile. And the concept of percentile is really closely related to the z-score, which we're going to talk about in a second. When we talk about percentile, something like the 95th percentile would be the spot under the normal curve where 95% of the area lies below that value. So if we think about this for a second, here at the mean, we know that 50% of the area lies below or to the left of the mean. We know that this area right here is 34% because we calculated it right here. So 50 plus 34 gets us up to 84. We know that this area here is 13.5, so 13.5 plus 84 would be 97.5. So right here, two standard deviations above the mean, we're in the 97.5 percentile, which means that the 95th percentile might be something like right here. So that might be the 95th percentile because that is the point under the curve where 95% of the area is below this line. So with that in mind, let's talk about the z-score because the z-score will give us the value in terms of standard deviations for any percentile that we want. So if we know that we're in the 95th percentile, we know that we're right at that point that's just above 95% of the data under the curve. And we can see right here that that's a little bit less than 2 standard deviations above the mean. What we'd like to be able to do is have a value, and this is going to be the z-score, that consistently gives us that spot, that 95th percentile, that spot where 95% of the data is below it, because that way we can always refer to that particular z-score, and we'll know that that is the point. Maybe it's 1.7 or so standard deviations because we can see where this is. That gets us to just above 95% of the data. So the formula that we use for the z-score is z is equal to x minus mu divided by sigma, where mu is the mean, so right here at the center. X is the particular point that we're interested in, so x might be this point right here, And so when we take x minus mu, the mean, we're really getting this distance right here, the distance between the mean and the point that we're interested in. And then we divide that by 1 standard deviation, which means that we're going to get a value, maybe like for this spot right here, something like 1.7, that will tell us that we're 1.7 standard deviations above the mean. So the z-score for a data point, x, is just how far that data point is from the mean in terms of standard deviations. So let's say that we know for some normal distribution curve that we have, let's say we know that the mean is maybe 16 and the standard deviation is 1. So a standard deviation of 1. And then we have the value 17.5. So let's say 17.5. And so what we do is we take 17.5, subtract the mean. So again, we're finding some distance here. We get 1.5. So we get 1.5 divided by 1, which is 1 standard deviation. And this isn't just 1 because we're talking about 1 standard deviation. We just assigned the standard deviation to have a value of 1. It could have been 0.8 or it could have been 2.7 or whatever. But we just said 1 standard deviation is 1. And so then the value we get here is 1.5. So 1.5 is our z-score. Then what we do with our z-score is we go to what's called a z-table. And this is going to look overwhelming at first, but you will use it a lot, so we want to get used to it. So what we're going to do is we're going to come here to our z-table, and we have this z-score of 1.5. So what we want to do is we want to go down the left-hand side here until we get to 1.5. So if we go all the way down, we get to here, 1.5. And then in our case, we just have 1.50. We don't have a decimal place in the hundredths, so it's just a 0. If we had, for example, 1.53, we would come across to the 0.03, and we'd look here, and then we'd come to the intersection. But in our case, we have 1.50, so we're looking in this first column here. So when we find the intersection of those two, we can see that it's this value right here, 0.9332. So what that tells us is that on a normal distribution here, if our mean is 16 and 1 standard deviation is 1, so this distance right here is a distance of 1, that's 1 standard deviation, and then we're up here at 17.5, so maybe we're right here at 17.5, then the z-score of 1.5 tells us we are 1.5 standard deviations above the mean. The fact that this value is positive tells us that we are above the mean as opposed to below it. So the z-score says you're 1.5 standard deviations above the mean. But in a normally distributed curve, 1.5 standard deviations above the mean is always going to have the same amount of area below that spot. In fact, according to our z-table, it's going to have 93.32% of the area below it. In other words, a z-score of 1.5 tells us that we are in the 93.32 percentile, or approximately the 93rd percentile, or that 93% of the area is below that spot. So it would tell us that if we come here to 1.5 standard deviations where our 17.5 is, that all of the area under the curve below that 1.5 standard deviations, so all of this is 93.32% of the total area under the curve. And keep in mind here that because the full area under the curve is 100%, if I want to find the area above 1.5 standard deviations above the mean, so everything here that's not shaded in green, I would just take 1 minus 0.9332, because 1 represents all of the area under the curve, and I know that everything to the left of 1.5 standard deviations above the mean is 93% of the area, or 0.9332, and I would just get here 0.0668, and that tells me that only 6.68% of the area is to the right here, or above 1.5 standard deviations above the mean. So I hope you're starting to see how this z-table standardizes the area under a normal distribution. Now remember we said before that a positive z-score indicated a value that was above the mean or to the right of the mean. Well, if we have a negative z-score, it indicates a value below or to the left of the mean. And that's because, again, going back to our example here, remember we said that the mean was 16 and we looked up a value of 17.5. So when we took 17.5 minus 16, we got a positive 1.5. But if we were somewhere down here, let's say at 14, below the mean of 16, then our z-score here would be 14 minus 16 over 1 is equal to a negative 2 in the numerator divided by 1, or just a negative 2.0. So notice how, because we found a value below the mean, we get a negative z-score. When you have a negative z-score, you want to look that up in the z-table with negative z-scores. Notice here we had positive z-scores on the left side, but here we have negative z-scores on the left side. So a z-score of negative 2, again, we come down here on the left to this point right here, negative 2.0. And again, because we don't have an additional decimal place, this is negative 2.00. We're just looking up this column right here. And the intersection of those two is this value right here, 0.0228. And what we need to keep in mind here is that z-tables always give you the area to the left of this particular value. So 0.0228, well, if this is our value here, 14, that 0.0228 is this area right here to the left of this 14. And we can see that that's 2.28%, or 0.0228. So we would say that 14 in this imaginary data set that we made up is in the 2.28 percentile, or if we rounded it, in approximately the second or third percentile, as opposed to, on the other end, the 93rd percentile, which we calculated for 17.5. And again, if we wanted to find the area above this value of 14, we would just take 1 minus this 0.0228. The last thing, though, that I want to mention is that we've done 2 examples now where we found a z-score. So we got a z-score of 1.50 and a z-score of negative 2.00, and we looked those up in our z-table by looking down the left-hand side here and then across to the appropriate column, finding the intersection of those, and getting a value from the body of the table. But we can also use z-scores in the opposite way. So for example, if I'm taking a test, maybe I'm taking the LSAT to try to get into law school, and I want my score to be in the top 5% of all test takers. If I know that test scores are normally distributed, and in fact tests like that are usually scored in such a way that they do follow a normal distribution, if I want to be in the top 5% of all test takers, that means that I want to be above the 95th percentile. So this time I could go to my z-table. Again, I want to be one of the top scores, which means I'm going to be on the right side of my normal distribution. I'm going to be up here in the high percentiles in the right tail. So if I look at the 95th percentile and I'm looking for 0.95, I can see that I find it right here. It's going to be somewhere right in here. Because what I notice is that when I have a z-score of 1.64, so this first value right here, 1.64, I would be in the 94.95 percentile, or just under 95%. But if I truly want to be in the top 5%, I truly want to be inside that top 5%, then 94.95 doesn't quite cut it, which means that I want this value right here, which gives me 0.9505. I am inside that top 5%. That's a z-score of 1.65, which means I could then plug into my z-score formula. So I know I need a z-score of 1.65. So if I plug into the formula, I could say 1.65 is equal to, and then if I just know the mean and the standard deviation of everyone who takes the LSAT, and I could maybe look up that data for a previous year, I would be able to plug in for both of those values. So then the only missing value, the only unknown, would be my actual score right here. So if I just plug in for mean and standard deviation, I would then be able to solve this equation for x, and I would know exactly what score I have to get in order to be in the 95th percentile, in order to be better than 95% of test takers. And so that's an example of how we would use the z-table in the opposite way, or working backwards, where we find a percentile or a value that's in the body of the table, and then look to find the associated z-score by following this across to the beginning of the row or to the top of the column.